Okay, so I've erased the board, put up a slide to motivate the discussion. So let's talk a little bit about minimizing the in-sample error. Okay, and this is a huge field it's called optimization. And we are not even going to touch the tip of that iceberg. So there are multiple courses, and you can even do a major in mathematical optimization of various kinds. Okay, now, first, a quick trick of the trade when you're training your neural network. You're trying to fit the error. Well, so your output node, is h of x is equal to theta of the signal SL, and then so this is what we call XL, and you fit that to the output that you see in the data. Okay. Well, and if you use this as the tan H, well, that's great. It's differentiable. You can run gradient descent, but there's a tendency for gradient descent to get into flat minima, flat regions which look like minima. For example, there it goes down, then gets flat, then goes down, then gets flat. That's typical behavior when you get into these what are called plateaus. Okay. And that's sometimes caused by the tan H function, because the tan H function becomes flat very quickly. So if you get to large weights, the tan H function is flat, so the gradient is basically zero, and so you don't make any progress. Okay. So, just like we did regression for classification, it's much faster to train regression. You can just remove this theta, and that means that the transform function for the output node is the identity. Okay, and so just like using regression for classification, you can train your neural network as if it's doing regression in order to fit the plus or minus one data. Okay. And that makes training usually faster. So that's a quick trick of the trade, trick of the trade that you should use in practice. Now, when you're done training the neural network for regression, you can put back the tan H and then train a little bit more. And then when you want to classify, you make this the sign. Okay. So that's a quick trick of the trade. Now let's focus on better algorithms. And what you see there is gradient descent in red. And then for as motivation, I'm showing you the queen of algorithms, my opinion, of course, which is conjugate gradient descent. It uses the same information as gradient descent, essentially, which is the gradient. But look how much better it is. And so let's explore a little bit this space between gradient descent and conjugate gradients, and see what kinds of simple enhancements to gradient descent can give us an improved performance. And at the end of the day, I'll tell you a little bit about conjugate gradients, but you can read more about it in the text. And of course, it's a famous algorithm. You don't need me to tell you about it. It's all over the place. Okay. So, what's the fundamental problem with gradient descent? And in general, iterative methods is you take a step at each iteration. And the question is what's the direction of the step? So question 1, direction of step. And we have more or less said that it's the negative of the gradient direction. Negative of the gradient. Okay, and then question 2, length of step. Okay, and we are using a fixed learning rate parameter. Okay, so in some sense, so we started with normalized gradient descent, which took a fixed step, and then we settled on gradient descent with a fixed learning rate eta. Okay. And what's the usual problem with fixing anything in an algorithm is that it may not work all the time. So if your error surface is nearly flat, okay, you want to take a big step. If your error surface is very steep, it's too dangerous to take a big step. It'll send you all the way to nowhere. Okay, so you want to take a small step. Okay, but in general, your error surface has both of these kinds of properties. And if you're far away, you want to take big steps. And then as you get closer to the minimum, you want to take smaller and smaller steps. Okay, now, when you start, you initialize the weights. You don't know what your error surface looks like. Okay, so you might start by taking a, whatever default step is. Let's say small. Okay, so the simple enhancement to gradient descent that I'm going to describe is so simple that it is effortless to implement, and it can yield huge benefit. Okay, huge benefit, and so you should implement it. It's called variable learning rate gradient descent. So variable learning rate. Okay, so what is variable learning rate? So you start and you check, did my in-sample error improve? So you started here and you took a step, and so you came here and your in-sample error improved. Okay, so if you improve E in, then eta goes to eta times some factor. Let's call it beta. Beta, for example, could be something like 1.03, 3% increase. So you will increase your next, the learning rate for the next step. So you'll take a bigger step next. Okay, and now you improved again. So you take a bigger step, and now you improved again. So you take a bigger step. Okay, and you take a bigger step. Okay, and now you're still improved. Okay, so you take a bigger step. You're getting better and better at this. You take an even bigger step. Okay, because you're increasing. Okay, and now you got much worse. Okay, you got much worse. And so what happens when you get worse? You went from here to here. So if you worsen the in-sample error, okay, then you shrink eta. Eta goes to eta times some alpha, where alpha is less than 1 now. Typically, we are, relatively conservative in the increasing, because you increase, so you get exponential growth. But when you shrink, you typically only shrink once. And so, we're very aggressive on shrinking. So you might choose alpha something like 0.8. So you really shrink when I increase the error. You can do one more thing. You don't need to stay here. So if you worsen the error, you can always go back. You can backtrack. So what you do is you backtrack and shrink this guy by a large factor, 0.8. So now maybe you'll move to here. Okay? And if you improved, you will increase from here. If you didn't improve, then you will shrink again. And if you didn't improve, you will shrink again and maybe come here. And now you're basically there. Okay? So variable learning rate, it very rapidly adapts the learning rate to your current situation and gets you to the minimum, usually very quickly. So it's a very simple enhancement to gradient descent. You just need to now maintain what's your eta, and you need to check whether you improved. If you improved, get more aggressive. If you got worse, backtrack and shrink eta and shrink it aggressively. Okay. But then, so once we've chosen the direction of the step, which is the negative gradient, you might wonder, well, why do I need to take a step? Why don't I just do line search? Why don't I keep going in that direction until I cannot improve the in-sample error anymore? Okay. And so that's called, gradient descent with line search. Gradient descent with line search. Sometimes I call this steepest descent. But, there's no fixed, well-accepted, terminology for this. Basically, there's no step size. No step size. Interesting. Okay. So let me describe that. Okay. So you don't need to now think about the step. You only tell me the direction. Okay, so you told me to move right. Okay, and I'm going to do a line search. So I'm going to keep moving right until I cannot improve anymore. And boom, in this example, I'm at the minimum. Okay, let me show you. So this is a very trivial example of what's going on in one dimension. Let me show you what's going on, let's say, in 2 dimensions. If you are trying to optimize 2 variables, and in general, we're trying to optimize a large number of variables. The perceptron is d plus 1 variables, but the neural network can have a large number, sometimes 1 million parameters, 1 million weights. Okay, so what happens with line search in more than 1 dimension? So let me show you line search in 2 dimensions. So line search in 2D. Okay. So you're at some weights. Okay, you're at some weights. Let me call it W at your iteration T. Okay, let's say the minimum is somewhere here. Okay, and for whatever reason, let's say the negative of the gradient. So the negative of the gradient. So let's draw contours of constant in-sample error. So let's draw some contours of constant in-sample error. So this is the optimal. Let me call this W star. Just to show you some of the geometry of, of what's going on. And these kinds of pictures are very important if you decide to go on and study optimization. So the geometry of what's going on is there are contours of constant in-sample error. So I'm drawing them. Okay. And depending on the actual error, okay, these can take on various different shapes. Okay, so now let's say your direction is the negative of the gradient. So can someone tell me where's the negative of the gradient? I'll give you a few seconds. Okay, 1, 2, 3, 4. Okay, and we discussed this, some time ago when we were doing constraint optimization. This is the contour of constant in-sample error. Okay, so the gradient is going to change the error in a maximum way. So that's the direction that changes the gradient the most, that changes the function the most. So it's going to move you as quickly as possible to the next contour. In other words, it's going to move you orthogonally to the current contour that you're at. So the gradient is going to be in this direction somehow. Okay, so where you're perpendicular to the current contour. Okay, so now if you do line search, you keep moving, and as long as you're going to lower and lower contours, you keep moving. So you'll keep moving, blah, blah, blah. Okay, and then once you get to this point, okay, now you see if you keep moving, you're moving to a higher and higher contour. And so this is where the line search will stop you. Okay, so you will move all the way to here. Okay. You will observe something interesting when this happens. So now you're at this point. The new gradient, okay, is in this direction, orthogonal to that. And the direction in which you are moving is tangent to that contour. So the new gradient is going to be tangent to your previous, is going to be orthogonal to your previous direction, and your previous direction will be tangent to the contour that you're currently at, the contour that you have stopped at. So this is just a picture of what's going on when you do line search. Okay. Now, in this two-dimensional situation, we did line search. It doesn't necessarily mean that we have come to the minimum. So now we take another direction, for example, the negative gradient, and we move in that direction, and we'll keep moving until we hit a tangent. We are tangent to another contour, then we move again, and we move again, and so this is line search. Okay. So the philosophy is great, no step, okay, but now we need to implement it. So previously gradient descent, you just compute the gradient, and you move. You compute the gradient, and you move. You compute the gradient, and you move. Okay. So each move is simple. But the gradient computation, especially if you're doing batch gradient descent, can be very costly. So you do all this computation for the gradient and you make one move. Okay. Now, in line search, we sort of do a little bit better. We do one gradient computation, okay, and then we move until we get to the minimum along this direction. So we don't need to compute the gradient anymore. We just need to compute the function, and we would like to get to this point with a small number of function evaluations. We are doing function evaluations to see at every step along this line search, am I at the minimum? Am I at the minimum? Am I at the minimum? So we need to efficiently get here. Otherwise, it's going to be very costly to compute the function many times. And indeed, there's a very efficient algorithm for line search. So let me show you the idea behind that algorithm for line search. So, this is a direction, so you're moving in one dimension now. Once you fix the direction, you're moving in one dimension. So let us imagine that the dimension in which you're moving is this. Okay? And, we're going to move an amount, let's call it eta star. So the function along this dimension looks, we don't know what it looks like, okay? But, let's say it looks, so we're moving in a certain direction, okay? And, let us assume for the moment that the function is decreasing in this dimension, and we want to quickly get to the minimum. Okay, so let's say the function looks something like this, okay, and we want to quickly get to the minimum. Well, we can't take small steps, okay? We're doing line search, okay? So here's what we do. We take a step, okay? Did we decrease? Yes, okay, we decreased. Okay, now double the step. Okay, did we decrease? Yes, we decreased. Okay, now double the step again. Okay, did we decrease? Let's say we doubled the step again, so we got here. So now did we decrease? No. Okay, and so I have come to a situation where I decrease, and then the first time I increase, I have come to a situation which I call a U. So I'm going to circle this point, I'm going to circle this point, and I'm going to circle this point, and you see it's a U. Okay. Once you come to a U, assuming the function is continuous, differentiable, and so on and so forth, we know that once you get a U, there has to be a minimum in this region. Okay, so you what's called bracketed the minimum. You bracketed it in this region. The minimum is between this point and this point. And now you can very efficiently find the minimum by binary search. Okay, for example, now you split this, okay, into two. So you try this point and evaluate the function. And one of two things happens. Either it's going to be lower than this blue point, in which case you've got a new U that's smaller, or it's going to be above this blue point, in which case you've got a new U that's smaller. So you've got a new range, then you bracket, you halve, and so on. Very fast. So that's binary line search. We can do it very efficiently. So typically in practice, maybe 5 to 10 function calls, and you've got to the minimum. Within some epsilon, within some accuracy. Then you do another line search. Then you do another line search. And you don't need to make your line search super accurate. Epsilon can be, let's say, 10 to the minus 5. Binary line search converges very fast. Even more efficient. Don't do binary line search. Fit a quadratic to these 3 points and go to the minimum of the quadratic. Oh man, that converges. And now and at that minimum, one of two things happens. Either you're below this guy, in which case you've got a new U, or you're above that guy, in which case you've got a new U. In both cases, you maintain this U, you maintain a bracket for the minimum, and you very rapidly shrink the length of that bracket. Okay? So line search is very efficient. Very efficient. So, let me erase and put on the slide a comparison of these various techniques that we have shown. So far, all these techniques are basically improvements to gradient descent, where the direction in which you move is always the negative gradient. And then, you can take either a fixed step, you can do SGD, or you can do variable learning rate, or you can do line search. Okay. So beefing up gradient descent. It's well worth the little bit of effort it takes. Okay, so in the picture, I'm showing you a comparison of gradient descent with variable learning rate and steepest descent, i.e. gradient descent with line search. Okay. And what we see is that once, line search gets out of the flat region, it takes off and does fantastically. So steepest descent and what we're looking at here is optimization time, not iteration number, because the iterations for steepest descent are more costly than the iterations for gradient descent and variable learning rate, because they just compute a gradient and take a quick step. Okay. Steepest descent computes a gradient, and then there's a line search to decide where to move. Okay. In the table, then we can compare steepest descent with stochastic gradient descent, and you see that stochastic gradient descent is slightly better. Okay, and so the current winners are, in some sense, stochastic gradient descent and steepest descent. Okay, and in both of these methods, let me tell you what's the difference. So, you compute a direction, and two, you make a move. Okay, so in stochastic gradient descent, the direction is the negative gradient for a particular data point. Okay, so this is negative gradient for a random data point x little n, and how much you move? Small step. Okay. For steepest descent, it's the negative gradient for E in, so the batch negative gradient, and how much you move? Line search. So you go all the way to the minimum along that direction, so line search. Okay. And so this illustrates that, two things. One, you can do quite well by, making the most of the gradient that you've computed by going all the way in the direction that you have decided to move in. And stochastic gradient descent suggests that, it's not necessarily always optimal to move in the negative gradient for the in-sample error. If you can quickly compute, a direction to move, there are other good directions, especially if you can compute them quickly.